In this lesson, we're going to go over data displays. Now, this section is very visual, and I have a lot of graphs and charts in the notes. So if you want a copy of the PDF, or maybe I'll post it in Canvas for this lesson so that it's a little bit easier for you to take notes on. So look for the PDF in Canvas so that you don't have to necessarily copy all of these displays into your notes. So we're going to talk about various types of data displays, and then after we do that, I'm going to go into some, I guess, just helpful practical information about data displays and some of the misuses of them as it relates to some of your homework problems, but also a lot of it's happening in the media and in the world around us as well. Okay, so first of all, the understanding of data displays. So we have a display here, and the display is showing that the murder rate is going up as shown by the x-axis, and so is the number of ice cream sold. So should we ban ice cream to reduce the number of homicides? Probably not. So if we're not interpreting this graph correctly, it could lead to false conclusions or potential misinformation. Okay, so that's why it's important to understand the visuals presented as it relates to data. So there's a few terms that you need to know for this section. First is the word frequency, and that refers to the number of times that the data value occurs. So in spring, when we first went into quarantine, I discovered TikTok. So let's say that I survey people and they tell me their social media app of choice. And let's say I get 3 people that say TikTok. Let's say 4 that say Instagram. And then Facebook, if that's still around. And so in terms of frequency, the number of users that prefer TikTok would be 3. So the frequency of that data value is 3. The frequency of Instagram would be 4, and the frequency of Facebook would be 1. Quantitative data refers to counts or measures. So here we're talking about numbers. So it could be like temperature, like 98 degrees or 100 degrees. It could also be like percentages in terms of grades, like a 73% or an 83%, so on. So quantitative has to do with counts or measures. Qualitative has to do with values in non-numerical categories or categorical data. So things like this could be letter grades, A, B, C, D, movie genres, food groups, seasons, spring, summer, winter, fall, things like that. So quantitative has to do with counts, qualitative has to do with categories, and then frequency is the number of times that a specific data value occurs. So moving into the types of displays, we'll see bar graphs, histograms, line charts, pie charts or circle graphs, and scatter plots. Okay, so first we'll talk about bar graphs. Bar graphs, the purpose of them is to display the frequency, how often, of qualitative data, so category. So how often a certain category occurs. The bars have meaning, so the bars represent the frequency of the data. So if a category is more frequent, then the bar should be taller. The least frequent category should have the smallest bars. So for instance, let's take the letter grades from an exam, again, not this class. A occurred 16 times, B occurred 1 time, C occurred 3 times, D occurred 1, and C occurred 7. So if we were to make a bar graph out of this data, we'd have each category along the x-axis, so A, B, C, D, and F, those are our categories, and the y value would be our frequencies. You can also have a tilted bar graph as well. So here we can see that A is just above 15, so probably 16. B is really low, C is under 5, D is under 5, and F is just above 5. Okay, our bars here are equally spaced. That's just because we have categories here. And then from the graph, we can see that the frequency, or how often F's occur, is less than the number or the frequency of A's occurring on the exam. So it's a visual representation of categorical data. Histogram displays the frequency. So frequency, I like to think of it as how often. Quantitative, so numerical, data occurs. The bars will touch each other, except for when you make your chart in Google, then they leave a tiny little space, but pretend the bars are touching each other, and that the width of the bars has numerical meaning. Okay, so when we're looking at this, we're still going to use kind of exam scores throughout this whole thing so you can see the differences here. But looking at both the chart and the exam score, so we have a range of 0 to 21. These first scores correspond to 0 to 21, so it should have a frequency of 4. So this bar is just below 5, so it's probably correct. Okay, or area of 21 to 42, there's only one value there. The area of, let me change colors here, 42 to 63, we've got 2 values there, bars taller than 1. And then the values of 63 to 84, the 1, 2, 3, 4, 5, and then the rest. Okay, and I'm just going to tell you that's 16. Okay, so these have numerical meaning. So the bars, depending on how the data is broken up, in this case, it looks like it's going up by about 21 each time. There's 21 of a width, but it doesn't necessarily, this width is a little bit bigger. It goes all the way up to 105. And then using the histogram, we can get some information here. So using the histogram, how many students earned at least a 63 or higher? So we're talking about 63 and above. Okay, so here, what we would be looking at for this, let's get a different color. How about pink? So here's where 63 is. So we're looking at 63 and above. So 5 and 16, because both of these bars represent grades that were 63 and above. So the correct answer here would be 21. Next, we have a line chart. Line charts are similar to histograms, except picture a histogram and placing a dot on the top center of each of the bars and connecting those together. So for instance, if I put a dot on the top and in the middle of each bar, I could connect those and I'd have a line chart. Line chart usually shows some sort of change in something. You know, as you can see, the chart is going up here, but for the purposes of this, that's how a line chart is constructed. It's still talking about numerical data and used to represent the frequency of the data instead. Time series graph. So if the horizontal axis represents time to demonstrate change over a period, it's called a time series graph. And so I actually pulled these numbers probably sometime in the spring of temperature in Fahrenheit versus time. So typically the x-axis is time, the dependent or the independent variable, and then what's depending on time, like the temperature, is typically the y-axis. Okay, so looking at this graph, we have the temperature decreases. Okay, if the graph is going down, it's decreasing. If it's going up, it's increasing. The graph is going down, levels out, goes down, levels out, goes down, levels out, goes down, and then starts to go back up. So this point where it goes down and then goes back up, or a low point, is a minimum, and a high point is a maximum. Okay, so what we can do is we can use this chart to answer some questions about patterns or trends. So let's go through each one of these and talk about whether it's correct or not. The temperature generally increased from 7 p.m. to 7 a.m. Let's see if that's true. So 7 p.m., 7 a.m. If I look at the graph is going down. So no, it's decreasing from 7 p.m. to 7 a.m. So anything that says increase from 7 p.m. to 7 a.m., I'm just going to get rid of now. All right, let's look at B. The temperature generally decreased from 7 p.m. to 7 a.m. Good. Rose to a maximum at 7 a.m. Well, 7 a.m. is a minimum, and then generally decrease. Nope. After 7 a.m., it goes back up. So B is not correct. Now let's check the validity of C. The temperature generally decreased from 7 p.m. to 7 a.m. Good. Fell to a minimum. Yep, that's the low point, and then generally increased. And so that's what we see from the graph. So at the time series graph, we can get some trends over time depending on what we're talking about. A pie chart or a circle graph is used to display percentages, or what would be called relative frequency. The sum of our percentages should equal 100%, and there has to be a label, or that should say key. A label or a key, and so to tell us what everything on the circle graph means. And so I have the chart here again, letter grade and frequency. When we talk about relative frequency, it has to do with how often that category occurs out of the total. So for instance, to get 57%, we would take 16 divided by 28 and then times 100. Same thing for B, C, D, and F. Okay, so here A is blue, B is red, C is yellow, D is green, and F is orange. And now these the slices should correspond to the frequency or relative frequency. So for instance, A is 57%, so we should expect the slice to be a little bit more than half. Okay, it wouldn't make sense to have a circle graph and say this is 50%. That's about a quarter. So the slices should correspond to how often the value occurs. Okay, you can also use these pie charts or circle graphs to discuss patterns in the data. So for instance, more students received F's than A's. Well, F is orange, A is blue. That's not true. More students received A's than B's, D's, than B's, C's, D's, and F combined. Well, that's true because that would be talking about this partial slice here, and A represents over half the data, so that would be correct. More students received B, C, or D combined than F. That's a little bit hard to tell. From the graph, we would be comparing, let me do B, C, or D. So we're looking at this compared to F. It's a little bit smaller, but this table could help you out. None of the others. Well, we found B to be true, so the answer here would be B. Scatter plots. So scatter plots compare two quantitative variables, so categories of numbers, let's say. And what the purpose of a scatter plot does is it tries to see how two variables might correlate or relate to one another. So for instance, if you were to plot a value on the x-axis and plot a value on the y-axis, that point represents the ordered pair or the two variables that we're talking about. In order to determine what type of correlation we have, you draw what's called the line of best fit through the data points. So essentially it's a straight line, y equals mx plus b, that gets as close as possible to all of the dots here. So for instance, with perfect positive correlation, our line of best fit would go through and all of the dots essentially fall on that line. Okay. For the second line, high positive correlation, it's saying as one value goes up, the other one goes up as well. And if we try to draw the line of best fit, and unless you're given the equation, you kind of eyeball it, I'm going to say it kind of goes through here where it hits some dots, but some dots are still a little bit above or a little bit below the line. Low positive correlation means even less are on the line, more around the line. No correlation means it's almost impossible to draw the line of best fit. Low negative correlation, or I guess let's start with perfect negative correlation. This means that as one variable goes up, the other goes down. So for instance, perhaps motivation over time, hopefully COVID cases over time, that as time increases, the number of cases decrease, okay? So it's perfect positive correlation if when you draw the line of best fit, all of your data points are on that line. High negative correlation, again, you estimate the line of best fit where some of the points are on the line and some are a little above or a little below. Low negative correlation, even more so, or around the line or not exactly on the line. These values under the graphs 1, 0.9, 0.50, negative 0.5, negative 0.9, and negative 1 are what are called the R values or the correlation coefficients, and we'll talk about those more later on, where R ranges in between 1, perfect positive correlation, and negative 1, perfect negative correlation. The biggest thing to gather from this is that correlation does not imply causation. So just because two values are correlated on a graph, that there's perfect positive correlation, let's say, does not mean that one caused the other. It could be cause for more questions, but it doesn't mean that one caused the other.